According to valence bond theory, covalent bonds form from the overlap of half-filled atomic orbitals. Unfortunately, the electron configurations I gotta do it. The electron configurations and directionality or geometry or orientation of pure atomic orbitals fails to account for the observed bonding behavior. Rather than sit strictly with these atomic orbitals, it was postulated that these bonds were being made by overlap of half-filled orbitals, but they weren't pure atomic orbitals. So mathematically mixed or hybridized atomic orbitals were then proposed as a way to explain and predict bonding. This hybridization as I said, is a mathematical mixing. Hybridization comes from what's called the linear, comes from, yeah, linear combination of atomic orbitals. The simplest hybridized orbitals are what are called the sp orbitals. Hybridization literally is taking the mathematical formula for an s orbital. So we'll have the mathematical formula for the s orbital, and then we'll do two things with it. We'll either add the formula of a p orbital, and let's, for fun, call it the px orbital. And then we'll also do the same thing, but we'll subtract that formula of the px orbital. That gives us two answers. So we're going to end up with two equivalent hybrid orbitals. Made by mixing so we could go S plus px and S plus, whoops, try that again, minus py. If we do that, we'll end up with two orbitals of the same energy. So that's what I mean by equivalent. They are degenerate. We end up with a little itty bitty tail on one side, and most of the electron density has been extended or pushed along the x-axis. So that's the greater extent of that hybrid orbital along the observed geometries. Of the electron pair geometries. Every electron group on a center atom is found with a hybrid orbital. Maybe a little bit of a funky way of saying it. Let me try this. If I have the linear electron pair geometry, so I have E, P, G, electron pair geometry is linear. That means that it is two groups. Means that there will be two hybrid orbitals. And these happen to be called SP. If I have the electron pair geometry of trigonal planar, that means that there are three groups, which means that there will be three hybrid orbitals. And these are called SP2. Tetrahedral. Four groups. You guessed it. Four hybrid orbitals. Oop. So four hybrid orbitals, SP2. 3. And of course, if you'd like, we can go to trigonal by pyramid. Which is 5 groups. So there's 5 hybrid orbitals, S, P, 3, D. And 6 octahedral when we have 6 electron groups. So we need 6 hybrid orbitals. S, P, 3, D, 2. Okay. Why hybrid orbitals? Why hybrid orbitals? The reason why we've gone to hybrid orbitals is to try to, account for the observed bonding behavior. Why do we see what we see? Again, hybrid orbitals have, I don't know, for lack of a better term, lobes of electron density extended along particular, I don't like that. Extended in certain directions to maximize overlap. Hybridized orbitals. So that's our directionality piece. Hybridized orbitals also account for lone pairs of electrons on a center atom. That's just awesome. All right, let's start working our way through some of this stuff, okay? So we'll go with BeH2. BeH2 is known to have a bond angle of 180 degrees. We know that BeH2 has 2 electron groups. If it has 2 electron groups, it needs two hybrid orbitals. If it needs 2 hybrid orbitals, I'm going to be mixing going to mix 2 atomic orbitals. Let's look at, excuse me. Sorry about that. Let's take a look at the orbital diagram for beryllium. And so for beryllium, let's see, I'll move it down here. Come on. S. In the case of making hybrid orbitals, we don't include quantum numbers. And so because we don't include the quantum numbers in making those hybrid orbitals, I'm going to not include them in my in my diagram here. So let's see. This is the p subshell, so px PY, PZ. Again, that's just convention. I could name it anything I wanted to. I could number it anything that I want to. And beryllium is in group 2. So it has 2 valence electrons. If I look only at the atomic orbitals, it doesn't have any half-filled shells. Or I'm sorry, half-filled orbitals. The bonds. And yet BeH2 exists. Okay, fine. Valence bond hybridization says you need 2 groups. You need to account for the connections of 2 groups. You're going to need 2 hybrid orbitals, which means you're going to mix 2 atomic orbitals. Okay, fine. Those are my 2 atomic orbitals I'm going to grab. And I'm going to put those through my mixer. And I'm going to end up with 2 new orbitals that are sp hybrid. Notice how I mixed one of the s's. I mixed the s with one of the p's. So s, there's a 1. P, there's a 1. 1 plus 1 is 2. How many electron groups am I accounting for? 2. How many atomic orbitals did I mix? 2. To give me 2 hybrid orbitals. And then I also have these unprocessed P, Y, and P, Z. And come on, I'm actually gonna do this. These are just a little bit higher in energy than the regular S. And I've got those 2 electrons to put in, and lo and behold, 1, 2. It fills up like any other degenerate set of orbitals. They half fill with parallel spins. So those are my 2 half-filled hybrid orbitals. Pointing 180 degrees apart. And so if this is my BE, and I'm going to go ahead and I'll draw my 2 hybrid orbitals in different colors just to differentiate them. And I'm also going to leave off that little tail, because it can get kind of confusing. Yep. All right. And then, yep. There you go. And each one of these has a single electron. And then there's my hydrogen with its little electron. Of course, nothing is drawn to scale. But there you go. Now we have the two bonds in a head-on fashion. Hybrid orbitals always overlap in that head-on or sigma fashion. Hybrid orbitals overlap in a head-on or sigma overlap. Okay, so I got those pieces. Let's try something else. Let's go for CH4. CH4, C, H, 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 H. All right, 109.5 degrees. So 4 electron groups. If I have 4 electron groups, I need 4 hybrid orbitals. And to get those 4 hybrid orbitals, I need to mix 4 atomic orbitals. Once again, taking a look at the orbital diagram for carbon, group 4. So here's S. And here's my P's, PX, PY, PZ. 1, 2, 3, 4. If I look at just what's going on with the orbital diagram for carbon all by its lonesome, looks like carbon can make 2 bonds. "90 degrees apart." Once again, not what we observe. Since I need 4 atomic orbitals mixed, I'm always going to start with the low one. I'm going to grab the S. So I'm going to grab all of them. I'm going to grab all of them, put through the mixer. I'm going to end up with 2, 3, 4 equivalent sp3 orbitals, because I grabbed the s and then all 3 of the p orbitals, and 4 electrons, 1, 2, 3, 4. Four half filled. Hybrid orbitals. To make 4 bonds. 109.5 degrees apart. You said this also can account for lone pairs. Let's look at ammonia. NH3. NH3. Come up with the Lewis dot structure and then make it into its pretty picture. Its trigonal, pyramidal, molecular geometry. Okay. 4 electron groups. Four electron groups. 4 hybrid orbitals. Means I'm going to mix 4 atomic orbitals. So once again, starting from our electron configuration, orbital diagram, what you would like to call it. There's S, and then there's the P's. So 1, 2, 3, 4, 5. Man, that's awesome, because it looks like, here's my lone pair. So it looks like I have 1 lone pair. and 3 bonds. That's fine. That's absolutely true. The problem is those bonds would be at 90 degrees to each other. Can't have it. 4 electron groups, 4 hybrid orbitals. I'm going to mix 4 atomic orbitals. And do the same thing. Here we go. There we go. So I'm going to mix them up. I'm going to get my 4 equivalent sp3s. 1, 2, 3. Now 1, 2, 3, 4, 5. This is my lone. Here's my lone pair. Here are my 3 bonds. Thing is that all 4 of these are at 109.5 degrees apart. Now, one more thing I want to share with you in terms of hybridization, and that's to go with the making of multiple bonds. Sigma overlap. Remember, head on. Or along bond axis. Overlap. And then we talked about pi overlap. The whole reason for hybridizing is to maximize overlap along the bond axes, along those lines where the bonds occur. Pi overlap is that side-to-side overlap. It is not directionally right at each other. Because of that, pi overlap, or side to side overlap, happens between unhybridized and it's unhybridized, in our case, p orbitals. There's another thing I want to bring up that I'm not sure I really did expressly before. Let's take a closer look at a p orbital. With a p orbital, try to draw it kind of like an infinity symbol. Half of the orbital is above, I don't know if you'd like to call it an imaginary line. I don't know if you want to call it that. Or if you want to say there's the nucleus in the middle, there's a node. Oh, stop that. Okay. So we have half of the okay, half of the orbital above. And then we have half of the orbital below. They're actually opposite signs. One sign is positive, the other side is negative in terms of that mathematical expression. So it's one orbital, just, and within that whole thing, we've got that 90% probability. But that 90% probability is going to split into above and below. So the node on top, or I'm sorry, the lobe on top and the lobe on the bottom. When we look then at 2p orbitals going through this pi overlap, I'm going to try to draw them relatively close together. What we have is then half of the overlap is between the top halves, and half of the overlap is on the bottom. Let's see if I can't make that so we could actually read it here. So half of the overlap's on top, half of the overlap on the bottom as I have it drawn there. So once again, sigma overlap, hybridized orbitals. Pi overlap, unhybridized. So let's look at, oh goodness, let's look at phosgene gas. Phosgene gas, one of the first mustard gases in use Nasty, nasty, nasty stuff. C, come on, let's try this again. CCl2O. Let's see, we got C, double bond O, that's two little lone pairs, and then Cl, that's Cl, boom, 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 boom. Happiness and joy, right? There we go. If we concentrate first on what carbon is doing, I see that carbon has 3 electron groups. Okay, and so 3 electron groups means 3 hybrids, orbitals. And then that means I need to use mix 3 atomic orbitals. So I've got S and I'll bring it here. And P. 1, 2, 3, 4. So when I say that I want 3 hybrid orbitals, what I really want in the case here, I need to make 3 sigma overlaps. So how can I make a sigma overlap? I need to have 3 half-filled orbitals. That's why when I grab the orbitals that I'm interested in grabbing, I'm going to grab the one that's empty and one of the other ones. Again, the only reason why I know that this is what I need to do is I know based on the structure that I have 2 single bonds and a double bond. Each single bond has a sigma overlap. Each double bond has a sigma and a pi overlap. So these are my sp2 hybrids. And then I have the p orbital that I haven't played with. And putting my electrons in, I have 1, 2, 3, 4. What we're doing is really just trying to put together a picture to explain what we observe. what I used to get so caught up in is, oh, so this is what happens. It goes from this, and then we actually have these 4 separate orbitals. 3 of them are this sp2 hybrid, and the answer is all of this is mathematical. All of this is a way to explain that within, in this case, phosgene, there are 3 sites that have to have this special directional overlap. And we're using this idea of hybrid orbitals to account for that. Right, so there's my carbon. And now I have 2 more of these, and I'm going to try to do this looking at the side. Try. So there's 1. And then I'm going to tuck this one. Oh my goodness, it's horrid. There we go. Tuck that one in behind. And then put my CLs in green here, or in red, green. Yeah, I can't tell colors even today. That's awesome. Okay, so there are my 2 CLs. And now looking at the oxygen, well, oxygen has a p orbit, has 2 p orbitals that are partially filled. So it's going to have oh, actually, I didn't want red. Do oxygen in a different color. Let's do it in green. There we go. There we go. And so this is my oxygen. And you could imagine then that there is an axis that runs right along in between the 2 chlorines through the carbon to the oxygen. So this is all in a single plane. Now here's my oxygen and then my carbon. I also have, with the carbon, I have, well, yeah, let's just do this. This is the sigma overlaps, right? And then we can do a picture that involves the pi overlaps. Here's my C. And so I've got, yeah. So I've got, come here. Come on. I've got my carbon. And there's my unhybridized p orbital. And then the oxygen, also with its p orbital. With half and half. And then this is the axis going between the two. So this pi overlap is occurring above and below. Half of the overlap's above and half of the overlap is below the plane of the molecule.